next presentation will be given by Dr. Malkhanov.
So, my name is Alexey Malkhanov, and today I will talk about magnetoelastic waves in a nonlinear electrically conductive solid micropolar medium. First of all, a few words about the mathematical model. So, the equations of dynamic of a micropolar elastic body with account of mass forces of electromagnetic origin can be written in the following form. These equations were obtained with the help of generalized Hooke's law, which are depicted below. Also, we take into account the components, the geometric relations for the components of the strain tensor and bending torsion tensor, where we account both linear and nonlinear terms. And these relations look as follows. In magnetoelasticity, it is assumed that the action of the electromagnetic field on the strain field happens through Lorentz forces, and the relation is written here. And take into account all these factors, we can derive the equations of dynamics of the micropolar medium with account of external magnetic field as following. These are two equations. And here are E, the electric field intensity, B is magnetic induction vector, G is current density vector, rho with index E is bulk density of electric charges, and vector F and G nonlinear include terms due to the consideration of elastic geometric nonlinearity. So from Maxwell's equation, equations from electric and magnetic inductions, inductions will be written as follows. These equations should be...
Я уже на конференции, я уже подключился, конечно, буду.
So, sorry, don't speak with...
Can you please mute your phone, your mic? Thank you. So these equations should be accompanied with electromagnetic equations of state. And here H is the magnetic field intensity, sigma is conductivity, epsilon with index E is absolute dielectric constant, and mu with index E is absolute magnetic permeability of the medium. In magnetoelasticity, it is assumed that we neglect by bias currents and suppose that there are no free electric charges. Taking into account all these factors and assumptions, our system of magnetoelasticity can be written as follows. Further, we will consider a one-dimensional nonlinear shear rotation wave. And let us suppose that our displacement and rotation vectors have only one non-zero component, as well as the vectors for nonlinear terms, F and G. With account of this assumption, the system of equation of magnetoelasticity will look as follows. Further, we will consider only ideal conductive materials. And in this case, the components of external components H1 and H3 of the external magnetic field are constant, and the relation between the second component of external magnetic field and the gradient of displacement will look as follows. Also, we can find the relation between the gradient of rotation component and displacement derivatives of the displacement with the help of the following relation. Taking into account all these factors, we can rewrite our initial system of magnetoelasticity in the form of a single nonlinear partial differential equation with respect to displacement. Here, C with index tau This is the speed with which the shear wave would propagate in the case of absence of rotation in the material, of rotation of particles in the material. And C with index phi, this is the speed with which the rotation wave would propagate in the absence of shear deformation in the medium. C with index A, this is so-called Alfvén wave velocity, which is proportional to the intensity of external magnetic field. And the rest of the coefficients have the following relations. For further analysis, we introduce the mentioned variables, and after that, our equation can be rewritten in the following form, where the term n with index 1, etc., 8 denote some nonlinear terms. And let us, and these terms have the following form, these nonlinear terms. And let us assess the order of smallness of this nonlinear term. Let us suppose that a nonlinear term n with index 1 has order of smallness epsilon, and based on this we compare the order of the rest nonlinear terms. And we came to the conclusion that the rest of the nonlinear terms have significantly higher order of smallness, and that is why we will neglect them for further analysis. If we return back to the initial dimension variables, the evaluationary equation can be written in the following form. We will seek for the solution to this equation in the form of traveling stationary wave, which depends on variable xi, where big V, this wave velocity, previously unknown, and taking into account this this substitution, the partial differential equation can be transformed to an ordered differential equation, which has the following form. And here U is shear strain, and M1, M2, this is the coefficients, and where the Q denotes the following polynomial. So we can judge we can judge about the existence of nonlinear stationary wave and their qualitative features by the signs of the coefficients M1 and M2 and the positive or negative definiteness of the polynomial Q. We can rewrite the equation in the following form. For that purpose, we multiply it on the term du divided on dxc, and we perform integration. And after that, the equation can be rewritten in the following form. And here, E, this is integration constant, meaning the initial energy of the system. Let us know that this equation allows the separation of variables. So we can rewrite it in the following form. And let us further suppose that the expression under the square root has three real roots that it can be expressed in the following form, where the roots have the following connection between each other. And after that, the equation can be written in the following form. The solution to this equation in this case can be either periodic or aperiodic. Aperiodic solution corresponds to spatially localized waves or solitons. So the soliton is described by a hyperbolic cosine, and expression is given here. And if coefficients for our equation are both negative, the expressions for amplitude and the width of this soliton have the following form. And in the picture, there is the shape of this soliton. In this case, this is the soliton of negative polarity. And also in this picture, we can see the dependence of its form on the external magnetic field intensity. And we can see that with the growth of the external magnetic field intensity, the amplitude of the soliton is getting bigger while the width decreases. In case when our coefficients M1 and M2, particularly M1 is negative and M2 is positive, the expressions for amplitude and the width of the soliton has the following form. And in this case, we deal with the soliton of positive polarity, and the impact of the magnetic field on the amplitude and the width of the soliton is depicted in the picture. And again, with the growth of the intensity of magnetic field, the amplitude is getting bigger while the width decreases. So here in the picture, there are depicted exactly what I have mentioned above, the dependencies of the absolute value of amplitude for both cases and the width. So with the growth of the external magnetic field amplitude, the absolute value of amplitude is getting bigger, while the width is getting smaller. So conclusions, we have studied a nonlinear model of an electrically conductive polar medium interacting with an external magnetic field. It has been shown that two factors will influence the wave propagation, dispersion, and nonlinearity. And the combination of these actions can lead to the formation of stationary waves that propagate at a constant speed without changing any shape. So that's it from my side. Thank you very much.
Thank you very much. Any questions, please? Do you have questions? Anybody? I don't see. Maybe. Oh no. Are there questions? I cannot see this in
Thank
the
you so
system.
much. We don't have any questions.
Okay.
We
So
don't have any
maybe one by myself, like a suggestion. Maybe not a question, a suggestion, because the analysis you perform is based on the traveling wave exact solutions. Maybe it would be nice to perform some numerical simulation also on the formation of such wave which you obtained analytically. Because this is these are particular solutions, traveling wave solutions, so, which satisfy specific initial conditions. What happens when the initial condition is different from these? Probably, say in the KDV case, for example, the rather arbitrary initial condition is split into the consequence of the solitary waves. Each of them is described by the traveling wave solution. Maybe something happens in your case also. Okay. This is like a suggestion.
Yes, the case is very interesting. What will happen with the different initial conditions, and of course, these simulations are needed to be done numerically. Of course, yes. Thank you for the suggestion.